In today's video, we're going to learn about the squeeze theorem in calculus. Now, the squeeze theorem is used to solve certain limit problems, and it also has a much better name than squeeze theorem. This theorem is also known as the sandwich theorem, which is objectively a better name than squeeze theorem, because we use squeeze in all sorts of things. When are you ever going to be able to apply a sandwich to calculus? What is the squeeze theorem? Well, this is a little bit easier to show with a visual example. Let's say we have a graph like this. Up here we have the function, something like that. It goes on from there to there, and this function is f of x. Now below it we have a function that looks something like this, and this function here is g of x. And between both of these functions we have the function h of x. It is between this function at all times. And let me write that out up in this corner. G of x up here is always less than or equal to h of x, which is always less than or equal to f of x. What about this can we do to help us solve limit problems? Glad you asked. Since we know that h of x is always between g of x and f of x at any given point, we know that at anywhere along this line, the limit of this function is always between these two, which helps narrow it down from literally infinity to a given plane. But more importantly, whenever these two limits equal each other, this is also equal to these two limits. There's two conditions the squeeze theorem must satisfy in order to be used to solve for a limit problem. Thing number one is what I just wrote over there. It has to satisfy this condition. G of x, our bottom function down here, must always be less than or equal to h of x, and h of x must always be less than or equal to f of x. That's condition number one, which we have satisfied here. It may not show up great in the drawing, but this h of x is always between f of x and g of x. And condition number two, the limit of x approaching whatever constant of g of x must equal the limit as x approaches c of f of x. And both of these limits must equal L. In other words, the same thing. And if these two limits equal each other, the limit of h of x is the same thing, because based on this rule, it will always be between these two. And let's just say that g of x is 2, and f of x is also equal to 2, this limit must equal 2. That's what the squeeze theorem is used for. If we know that h of x always lies between these two functions, we can find a point where h of x must equal these two. And this will probably make a little bit more sense when we do a mathematical example. So let's get started. I'm going to leave these conditions up here on the side so you can look at them while we do the problem. So the example we're going to use today is the limit as x approaches 0 of x squared times sine of 1 divided by x. What is the limit of this function? Well, at a glance, we're not just going to be able to solve it just by looking at it and be like, oh, it's just 3 times 2 equals 6. No, if we plug in this 0, we're going to get an undefined function here because we cannot divide by 0. So we're kind of stuck. So how may we go about solving this problem? Well, I want you to notice something. We have this outer function, and we have this inner function, x squared and sine 1 of x. And more importantly, I want you to notice this function. The function of sine of x looks something like this. Let me get my blue pen out so you can see the graph a little better and extend this way over here. So this is what the function of sine of x looks like. It just goes up, comes back down like that, forever and ever, going both ways, but I only need to draw it on one side. The highest this function will ever get is y equals 1, and the lowest this function will ever get is y equals -1. That is the balance of the sine of x equation. And as you can see, we are squeezed between two numbers, and we can apply the squeeze theorem to this problem. So I'm going to erase this graph so I have a little bit more room, and let's solve the problem. So based on the graph we just had up here a minute ago, we know that sine of 1 over x will always be greater than or equal to -1. Sine 1 over x. And let me make that look more like an S. That looks like a G. Sine. Okay, and based on the graph, we also know that the sine of 1 over x function will always be less than or equal to 1. So this function, this inner function here, sine of 1 over x, will always be between these two values. So now we've narrowed it down from -infinity to infinity to -1 and 1. That's a couple less numbers to work with. But you may notice that this actually isn't the function we have in our limit. We have an x squared times sine of 1 over x. So how can we change our sine of 1 over x to equal what we have up here while also not changing what it's between? That's right, we can just multiply everything by x squared. So we got to apply it to everything. -1 times x squared is -x squared, which is always less than or equal to x squared sine of 1 over x, which is always less than or equal to x squared. And at this point, we can actually solve the problem. How are we going to do that? Well, we can plug in our x value for x squared and x squared. So we know that the limit of negative x squared as x approaches 0 is just negative times 0 squared, which is always less than or equal to x squared sine 1 over x, which is always less than or equal to, plugging in 0 here, 0 squared. And you may notice that negative 0 squared is just 0. And you may also notice that 0 squared is just 0, which means that this function, let me just bring it over here, apologies, I kind of ran out of room down there, is equal to 0, which is less than or equal to x squared sine 1 over x, which is always less than or equal to 0. And well, these are the same. We've squeezed this function between two other functions, which means that this must also equal 0 in order for this to be true. So this limit is actually equal to 0. And that is the limit of our problem. I hope this video helps you out understanding the squeeze theorem. I know it's a bit of an odd theorem, but the more practice you get with it, the better you'll get at it. I'm going to link a video that has more examples of the squeeze theorem up here. It's not one of my videos, but it's really helpful and helped me back when I was taking Calculus 1. If you want more Calculus 1 help, consider subscribing to the channel, as I'm going to be uploading every single lesson in Cal 1 that I learned in college. I'll see you guys in the next video.